Okay, in this recording we'll work a couple of more examples. Let's start with this one. This one is an interesting toy. What you do, you cock the toy, it has a spring, you kind of push it down on the floor and it kind of jumps upwards. Now, in this case, what do they give us? A 0.1 kilogram toy. And the spring that you are going to cock has a spring constant of 1,000 newtons per meter. And it seems when you push it down, you are going to cock it. We are going to compress the spring by an amount of 20 centimeters. Now the question is, what is the mechanical energy of the toy when sitting on the floor with a cocked spring? Okay, that's an interesting thing. Now remember what the expression for mechanical energy says. It is EP plus E kinetic energy. Now in our case, we have a spring as well as gravity, since the toy is going to be able to move up and down. Whenever we have something that's capable of moving up and down, we need to use the gravitational potential energy. And then whenever we have a spring, we need to use spring potential energy. So our expression changes into EPS plus EPG plus EK. Okay, now at ground level, we use that as reference. Bottom position of toy. Then when we do that, that makes our gravitational potential energy at that level to be equal to 0. Now, when the spring is cocked, the toy is ready for launch, then, sorry about that, then my spring potential energy is given by 1/2 of kx squared. Now in this case, that's going to be 1/2 of 1,000 newtons per meter times the 20 centimeters, which is 0.2 meters squared. Okay, now we need to calculate that. 0.2 squared is 0.04. 0.04 times 1,000. That gives us 40 divided by 2. That gives us 20 joules. So our spring potential energy is 20 joules. And the toy there is cocked, it didn't start moving, so its kinetic energy is equal to 0. So what that tells me, the mechanical energy of the toy at that initial position is going to be the spring potential energy 20 joules plus the gravitational potential energy 0 plus the kinetic energy 0. So overall it is 20 joules. That's my answer for part A. It required a lot of work. Now, question B. What will be the mechanical energy at the highest position? Again, assuming no losses due to air resistance here. So then, in that case, it's conservation of mechanical energy, so it should be equal to 20 joules. That's easy. Now, part C, it says, how high does the toy jump? Okay, when they tell us that, we are going to examine our mechanical energy at the top. What's going to make up our mechanical energy at the top? So remember what we said, this is our toy with the spring cocked initially. Then it's going to be on top here. Now the spring is not going to be cocked anymore. So my mechanical energy is going to be made up of what? Again, EPS plus EPG plus Ek. Now, at the topmost position, the spring is not be compressed or stretched. It's going to reach equilibrium position. It's stretched to equilibrium when the toy was coming off the ground. So then my spring potential energy is going to be 0. No compressed or stretched spring. My gravitational potential energy relative to ground is going to be mgh. We don't know it, since we don't know what h is. My kinetic energy, when we are going to be on top, is going to be 0, because that's the topmost position. That's when the toy is going to momentarily stop. So what that tells me is that mgh, or the gravitational potential energy, is going to be equal to my overall mechanical energy. It's going to be equal to 20 joules. So we can solve for h from there by dividing both sides by mg. So h is going to be 20 joules over mg, which is going to be 20 joules over, in this case, 0.01 kilograms times 10 meters per second squared. So 0.01 times 10, that's 0.1. So 20 over 0.1, that gives us 200 meters. Man, this is quite a powerful toy. This would be dangerous for a kid. 200 meters is quite high a distance, about 200 yards. Okay, but anyway, you get the idea. You get the idea of how to solve this particular problem, I hope. Okay, now let's go to the next question. In this question here, we have a block down an incline. We have no friction. Probably you remember seeing this type of setup earlier. Now the question here, what is the mechanical energy of the block when it is at the highest position? Okay, now when they don't tell us the reference point, we can choose it by ourselves. Okay, I'm going to choose it in this case as this bottom point here. Now, when it is at the highest position, it's starting from rest, so its kinetic energy is going to be equal to 0. Now, it's there is no spring, so we don't have to worry about spring potential energy. But the gravitational potential energy is going to be given by mgh. Now, what would h be? H is going to be the height relative to the reference point. So it is the height. It's not d. It's how high are you. And how high are you in this case? That's L. This is how high are you. So EPG at that point is going to be equal the mass times g times 3 meters. And mass times g is the 100 newtons here. So 100 newtons times 3 meters, that will give us 300 joules. That's our EPG, and since the kinetic energy is 0, our mechanical energy then is 0 plus 300 joules. It's 300 joules. Now, the question then asks, what is the kinetic energy of the block when it moves the distance d shown? Okay, now to get that, we remember that mechanical energy at the bottom is going to be the same as the mechanical energy at the top. So mechanical energy at the bottom position is going to be 300 joules. And we also remember that at this level, that's our reference point. So then the gravitational potential energy there is equal to 0. So that means my mechanical energy is going to be, remember, EPG plus EK. So it's going to be 0 plus the kinetic energy. And since we don't have a gravitational potential energy, that tells us then the kinetic energy is equal to EM, the mechanical energy, which is our 300 joules. Then the question, what is the speed of the block then? Then that becomes easy. If we know the kinetic energy, the kinetic energy is given by 1/2 of mv squared. So that's going to be equal to 300 joules. I need to find the mass that I never found. The mass is going to be Fg over g, which is going to be 100 newtons over 10 meters per second squared. So that gives us 10 kilograms. And then here, V squared is going to be 300 joules over half of m. I divided both sides by half of m, so 300 over 5 kilograms. So that would give us 60 meters squared per second squared. And we take the square root of that. That will give us 7.75 meters per second. That would be, I need to write it separate since this is saying V squared. So V 7.75 meters per second. And that's my answer.